volumes of revolution. So let's look into the 7.2 volumes of revolution. And we talked a little bit about this last week, but I know it's a 3-day weekend, so who remembers anything? Revolution. Volumes of revolution. Let me just remind you of the process here of what we have talked about so far. Recall, if you have an equation, or I should say a function, and you spin it around an axis, you create a volume create a volume out of circle slices. So what we've done here is say we have a graph, right, of f of x from A to B. And we revolve this around the x-axis, right? We rotate this function around the x-axis. We created, what we did last time we discussed, we created a bunch of circles, right? This here is the radius of the circle. Right, from top to bottom. And you have and you have all kinds of circles that you create using this shape. You create these circles here. And this f of x is the radius, equals r. I should say f of x is equal to the radius of this circle. Some location point here, right? That location, the height of the graph is the radius of the circle from the 0 point, from 0. And so what we talked about was that the area of the circle, right? The area. People coming in or not? Never mind. The area of the circles. Was pi r squared. And to find the volume, you integrate the area. To find volume, you integrate from A to B of all the circles, dx. And so the volume ended up being was the integral from A to B of pi, basically times f of x squared dx. So it's the integral from A to B of pi r squared dx. But r, we know that r is the radius, which is the function, the height of the function. And so basically we create this integral of all these circles using this, this integral formula. And that's how we can calculate the volume of this shape. We know the function, we know the various heights of the function, we know that they create this circle shape, and we can create a volume by integrating all these circles, like sliced throughout this shape from start to finish. And we do an integral of that from A to B, and we generate this volume space, right? So an area is a cubic area, pi r squared, integrated across a dx. So we create a cubic volume by doing this integral. So that's what we discussed yesterday. We're going to practice some of this. We're going to look at some of this, and we're going to look at one more style of this, of how to do this with a little bit more complicated shapes. Basically, this idea here is called the disk method. Disk method. Because you are creating a bunch of disks, right? Flat, circular disks that you integrate along, like you're stacking these disks on top of each other to create this volume 3D space. All these disks you create. And you can also do this, of course, if you have a graph in the y direction. Like we said before, right? If you have, let's say, this equation here, and let's say you want to integrate around the y-axis. Let's say this is an f of y function, and you want to spin it around the y-axis. Right? From, let's say, from A here to B here. You have these slices along the y-axis, and you're creating the integral from A to B from below, right? So again, here we have the or in the y direction. I can do this. X direction, and if you want to do the y direction, it's the same thing, pi from, well, really we call them C to D, but whatever, A to B, it doesn't matter, of f of y squared dy. Let me replace this here. This is volume, same thing, it's volume. You can also do this in the y direction. You can integrate from, if you spin it, here you're spinning the graph along the y-axis. Spinning on the y-axis. So there's two kinds of ways we can create these 3D shapes: x-axis spinning and y-axis spinning. And they can, create different kinds of shapes depending on the directions that you spin them. Either way, you need a function. You need this function. If it's a function in terms of y, you use the f of y. If it's a function in terms of x, you use f of x. And the direction that you're spinning it. If you're spinning it along the y-axis, you need f of y. If you're spinning it on the x-axis, you need f of x, depending on the direction of your integration, right? If you're integrating across in the x direction, you need an x function. If you're integrating in the y direction, you need a y function. Right? That's how these work. So those are the disk methods, right? You're stacking these disks, so you're laying these disks side by side. We can sometimes have more complicated looking shapes. Not super complicated, but it's basically the same idea. This is called the washer method. Oopsies, washers. Washer method. And it's not really different, it's just we now have two equations. So this is with two equations creating a hole in the middle. So with the washer method, let's say we have, I don't know, here's an equation, f of x, and here's another equation. Oops, let me do it like, what's a good one here? Let's go, I guess, like this. G of x, right? And we want to go from A to B. Or let me try to draw this a little bit better. This is fine. This is fine. All right. So what we're going to do here is basically when you create this 3D shape, if we imagine spinning this along the x-axis, rotating around the x-axis, you're going to have this outside ring, right? Whoopsies. Outside ring. This is your outside ring. And you're also going to, let me do this in green. You're also, here's the green one, here's the blue one, outside ring, right? Going up to f of x. This is f of x. And the inside ring you're going to have is g of x. G of x. And that's going to be a little smaller. So I'm going to make this, right? G of x. And so what you're going to find is what you're creating with this shape here. Let's see if I do this in blue and do this in green. You're going to create this 3D shape that's like a donut, right? It's got an outside part and it's got an inside part. So you've created this sort of 3D shape, right? You have these rings here, and all of this part. Let me do this in red, maybe. All of this part is the volume, right? All this part's the volume here. It doesn't really look good. Basically, you've got these holes in the middle of this donut shape, right? You've got this empty space in the center here that has this, right, this sort of empty space here in the middle. And you've got your holes on the outside, right? Your sort of shape on the outside. Creating this sort of, oh goodness gracious, bad drawing, bad drawing. Donut looking thing, right? Basically, let me see if I can draw this a little better. So it creates your outside ring, right, across to a bigger shape like this. And you've got this hole in the middle, right, this hole here. This empty space going through, like a toilet paper tube, right? You get the idea. So to do this, to find this volume, it's basically you have the volume of this volume is going to be, well, let me go back. Let me go back. The area of this shape here, the area, is going to equal, well, it's basically the outer ring minus the inner ring. The outer circle of this shape, right, minus this inner circle to cancel it out. And so it's going to be pi times f of x squared minus g of x squared. Or I should do r1 squared minus r2 squared. But those are basically, basically f and g, same idea. R1 and R2, right? R1 is the outer ring, right? This is R1. And g of x is R2, the inner ring. So it's basically the pi times f of x squared minus g of x squared dx. And you integrate that from a to b, and that creates the volume. So it's the same idea. It's just now you have these two rings instead of one. Here's R2, and this bigger ring out here is R1. So you take your outside ring minus your inside ring. Outside function minus your inside function. And since they're both, you're doing an integral of circle areas, you have two circles that subtract each other. Pi r squared minus pi r squared, you factor out the pi, you have the pi on the outside, and so it's basically the outer circle minus the inner circle, both of them squared. Both of them squared. So let me give you an example here of how we can do this. And this is called the washer method. This is for washer method. And we call them washers, washer method, because, if you have like a bolt and you have a washer on the bolt, it has an outer ring and an inner ring, right? It's like a thick, if you've seen a washer before, it's got this thick ring around it, right? You can call it a donut method if you want, same idea. It's got an outer part and an inner part, and you kind of cancel them out. You have this washer. And you're stacking these washers of different sizes together to create this 3D object with a hole in the center. So you're creating this hole by subtracting. So the principles are pretty straightforward. You just get a bunch of circles, create these circles, and integrate those circles along a distance. And again, you can do the same thing with a vertical integral, but I don't think we're going to get into that. But here's an example. Find the volume of the region rotated about the x-axis contained by these two functions. Y equals x squared and y equals 2x plus 3. And let's say x equals 0 and x equals 5. No, let's not say that. Let's not say that. Forget this. Find the volume contained by this equation here, contained by the following two functions, rotated about the x-axis. Find the volume of this shape. So the way we're going to do this problem is very similar to the way we did the problem before when we had a region contained by the area, right? First, we want to find the area of the region. So we're going to graph. Use this graph, and of course use Desmos, to see the picture of what you've made. So let me share my whole screen here again, and let's get into Desmos. If you need the equations, here we are. We have y equals x squared. Y equals, let's call this f of x. Capitals? No, stop it. F of x equals x squared. And g of x, let's call this g of x, equals 2x plus 3, right? That's the 2x plus 3? 2x plus 3. So here's the region. Here's my region. From 0, from -1 to 3. So I have my region contained in this sort of zone in here, is what I want to rotate this shape. I want to rotate this shape here from -1 to 3 around the x-axis, and I'm going to get this big, kind of like weird looking, I don't know, bulbous shape here. It's going to look kind of weird. It's going to look like a weird, like, I don't know, some kind of weird shape. If I get this three-dimensional shape, I rotate that around the x-axis. I'm looking for that volume. Okay. So let's try to draw this. And let's see if we can calculate the volume of this three-dimensional shape. So when I graph it, again, draw a sketch. Draw the sketch here. I have my line 2x plus 3, 1, 2, 3, going to go like this, and like this. And then my function x squared looks like 3, 2, 1. Looks something like this. Whoopsies. Something like that. Good enough. So I know it goes from up to 9, 3 comma 9. And this is negative 1 comma 1 right there, 3 comma 9. So I know my bounds of integration, and I want to find the volume of the region rotated about the x-axis. So my rotation is happening on the x-axis here. And I want to create this little 3D shape here, looking something like this. Looking something like that. A kind of truncated cone. Now this one has a hole in the middle because it's got two equations. So I'm going to have to figure out, right, I got my inner circle, my outer circle. So my outer circle is the blue. My inner circle is in green here. And that's my parabola there. So I got my outer circle, my inner circle. I have, this is going to be R2, and this is going to be R1. Because your outer circle, this is R1. Your outer circle is the one, just like how it's top minus bottom, same thing in this function here. Same thing in this function here. Angel, did I see you come in? Angel, welcome. So how are we going to find the volume? Are we going to use the disk method or the washer method? Basically, they're the same method. It's just one has one equation and one has two equations. So is this a disk or a washer method? Everybody in the chat, someone tell me. Disks or washers? What does this use? Let's look at our situations here, right? Disk method like this with one equation, or do we have to use the washer method with two equations? Anybody in the chat have an opinion? Disk method or a washer method? No one has any opinions? Well, looking at this equation, do we have one equation or two? Clearly we have an outside. Now we have this outside equation, this 2x equation, and this inside equation, our squared equation. So we're going to have to use the washer method here to create these two shapes that will, create this 3D shape here with an outer ring and the inner ring in green. Outer ring in blue and the inner ring in green. So we're going to have to subtract them. So let's set up this equation. It's very easy. Volume equals the integral from your starting to ending. So from -1 to 3. You start at -1, go to 3, right? If we look at our graphs here, start at -1, go to 3, right? Use Desmos, very handy Desmos. And we're going to integrate, put the pi on the outside. It's pi r squared. We're doing a bunch of circles, pi r squared. And we do, let's see, the outer ring is 2x plus 3 squared minus the inner ring, which is our x squared. Put that whole thing in a parenthesis, dx. And that's your formula. This equation here will get you the volume of this shape. If we want to simplify a little bit, let's see. From -1 to 3 of, let's see, 2x3 squared is 4x squared plus, let's see, 6, 12x plus 9 minus x to the 4th power, because x squared squared, right? dx. Right, to do that I just did 2x plus 3 times 2x plus 3. Right, when you square something, you write it twice and you do the foiling. It becomes this thing here. 4x squared plus 12x plus 9. Little trick, by the way, if you do square your first piece, 4x squared, square your last piece here, take the 2 times the 3 times the, 2 times this, gets you the middle piece. 2 times 3 is 6, 6 times 2 is 12, 12x. That's the middle piece. Little trick of how to spread these out quickly. Square your first piece, 4x squared, take the 2 times the 3 times the first piece, 2 times 3 is 6 times 2 is 12, 12x, plus the last one, 9. Last one squared, minus 4x. And then we integrate that, and again we go to Desmos. Integral from -1 to 3, and I'm going to leave pi here. And I'll do, let's see, it's g of x, so g of x squared minus f of x squared. Put that whole thing in a parenthesis. And do dx. And there's your answer, 227.87. If we took away the pi, 72.5 pi. Sometimes they leave the pi, sometimes they have an answer, but either way is fine with me. So this answer would be about, oops, don't forget your pi. What did I say, 227.87? 227.87 cubic units. Units cubed. Or just, we don't need the units, I guess. Or, what did I say without the pi? 72 point something pi? 72.53 pi. 72.53 repeating pi. Sometimes they leave the pi in the answer, sometimes they have an entire decimal. Either way is fine. But you want to use Desmos once you set up the equation, same thing, just use Desmos to calculate your answer. Can you imagine trying to do this by hand? I mean, it's possible to do this by hand, right? Okay, that's going to be 3, let's see, x cubed, this will be 4 over 3x cubed plus 6x squared plus 9x minus 4 to the power over 5. I'm going to plug in my 3 and then plug all that in, plug in the -1, plug all that in, do subtraction. You're going to get these two answers if you try to do this whole thing by hand. I mean, again, it's possible to do by hand, but if we can make it in a calculator, way easier, way easier. So, question about this process here. Find the volume of the region rotated about the x-axis contained by these equations there. Now let me throw something else at you. What if, instead of rotated around the x-axis, we rotate it about a different axis? B. Rotated about the line y equals 3. So part A rotated about the x-axis, but if instead of rotating it around a particular it's at the axis here, we can sort of move our rotation axis to anywhere. Here's what I mean. If we were to rotate about the line y equals 3, let's draw the graph again. And here's our equation here. Oops, goodness gracious. I'm trying to draw this a little bit better. Here's our equation here. And here's our line, like here, Here's the point 3, comma 9. Oh, sorry, y equals 9, not y equals 3, y equals 9. Equals 9. And here's our point negative 1, 1. If I were to imagine my rotation axis being right here, and I spin my graph, oh, I should have done this lower. Hold on, move this. Magic of technology, everybody. Let me move you down here. If I was to rotate around this axis here, so I spun the graph not on 0, but on y equals 9, this equation up here, y equals 9. I would get another 3D shape, right? And I would spin it. Let's see, I would have this would be my outer ring like that, right? And this would be down here. And then I'd have my inner ring being this, it's sort of like come to a point here. My outer ring would turn out to be this squared equation here. This parabola would be the outside part. And the inside part now would be this line here coming through the inside part. See what I mean here? Let me try to draw this a little bit better. I'd have this inside part, which would be the linear equation, and the outside part would be the parabola. So I have these rings now. So when I'm rotating around a different position, which one is the top and which one is the bottom depend on the perspective of the shape. So now the outer ring is the y equals x squared equation. And the inner ring is the y equals 2x plus 3 equation. Put this in quotes, inner ring. And so depending on where you're rotating, it matters what your equation is doing. Right? So to do this integral now, we got to go from -1 to 3, still doing the across the x-axis, right? But now we have this this line here that we have to deal with. So how do we deal with that? Hold on, let me just. So how do we do this situation here? We're going to want to do the integral of, let's see, yeah, the upper part minus the lower part rotated about that axis of 3. So how do we find the basically what's the size of our rings here is the question, right? What's the size of our rings? Our rings are going to be the outer ring, right? The outer ring is from 3 down to the height of our graph. I'm going to do the outer ring in blue. Outer ring is from 3 down to the height of our graph, right? So the outer ring is going to be 3 minus f of x is the radius of the outer ring. The inner ring is going to be inner ring, R2, is going to be 3 minus g of x. So we create this new function where we have this these different rings here, the outer ring an inner ring. You look at your graph, you determine the radii of the shape you're looking at, starting at your line, starting at the line, minus the graph you're trying to go to. So we do our volume integral here. The volume is going to be pi times the integral, -1 to 3, of 3 minus x squared minus 3 minus 2x plus 3 squared dx. So let's plug that into Desmos, everybody. Pi times, this is 3 minus f of x, that whole thing squared. Let me erase this. Integral pi from -1 to 3 of, let's do 3 minus f of x whole thing squared. Great. Minus 3 minus g of x whole thing squared. Whole thing taken to a, oh goodness gracious, undo that, thank God, a dx. -26.8. 3 minus, oh I see, because it's, oh I'm sorry, what, 3, 9 minus, there we go. I keep getting by the 3. Sorry everyone, not 3. Our equation was y equals 9. 9, and 9. Which again, our volume now was 375.3. 375.3. So when you rotate around the x-axis, you use the functions themselves. When you rotate around anywhere else, you're going to have to deal with this subtraction situation. If you have some other line that you're rotating about this other line here, you're going to have to do this subtraction situation. So as a rule, let me do this here. When you rotate around a line, your new functions, the radii, or the functions, they change. Functions change. Let me say functions change. Functions become the, how do I say, the number, the line, minus the function. So whatever your, or maybe I should say rotation axis, your axis minus your function. So take your axis of rotation minus the function, and you get your new radius. Whatever your rotation axis is located, subtract it from the function. I guess that's if it's above. If it's below, it's the other way around. Function minus axis, but if it's above, if the axis is above, if the axis is below, it's f of x minus the axis here. All right, not sure if that was helpful, but I want to show you these different situations that you may come across. Rotating around. Just take the shape into account. What you're really looking for, no matter what the situation is, what you're really looking for is the radius of the circles. The radius of the circles is what you want to find. And to find that radius, you start, if you're starting at the line, you take that line minus the length of the function that you're getting to. Or if your radius is above here, you take the function minus, well, this time it's minus 0 because you went down to the axis, right? So we did this minus 0, it's just we didn't write it down. Our radius was still the function here minus 0, or the function here minus this other function. One function minus the other function. Okay. So what I would like you to do is try some of these. So outer radius minus the inner radius squared. Integrate from a to b times pi, because you're doing a bunch of circles, pi r squared. Try these out. Your assignment. 7.2, page 461. I'd like you to do numbers 5 through 12. 5 through 12. Draw them and use Desmos. Actually, 5 through 13. 5 through 13 all. Draw and use Desmos. And then I want you to try number, what did I say, 57? 57. And 57. That's what I want you to try. Five to 13 all. Draw and use Desmos to calculate the volumes. And try number 57. We'll go over this next time, everybody. But thank you for your time today. Hopefully this was helpful. Or at least interesting. Creating these 3D shapes. We'll see you all on Thursday